I'm super excited to be here. Thank you all for having me. My name is Sean Gillespie. Thank you to ClickHouse and for StatSig for hosting us today. And thank you all for coming out and going to talk ClickHouse with us today. So my name is Sean Gillespie. I'm a staff software engineer at Temporal, based here in the Seattle area. And just before we get started, just a little bit about myself. I am a staff software engineer at Temporal Technologies. Before I worked at Temporal, I went to school in Atlanta, Georgia, born and raised. Went to Georgia Tech, which did great in football this weekend, if anyone's a college football fan. Yeah. Yes, wherever that was. Yes. Previously before Temporal, I worked at a couple different companies. I worked at Microsoft on .NET CLR, if you ever used .NET. An infrastructure as code tool company called Pulumi. And I worked at Facebook right before coming to Temporal. And I live in Capitol Hill, which is just right across the river here. So I'm super excited to be here to talk. And today, I want to talk a little bit about Temporal before we get into it. So Temporal, just a little bit of a background to kind of motivate why we're talking about observability. What we're going to be talking about. Temporal, as a company, we have an open source distributed system that we sell as a cloud offering, and also one that you can run locally. And at its core, it is what we call a durable execution platform, where the idea is that you write a program that you run yourself, and it communicates with our distributed system to get some guarantees around consistent delivery of parts of your logic. Like if you want to write a large asynchronous workflow of a bunch of different operations that you'd like to all happen in order, and you want to be really sure that they're all going to finish and be successful, the Temporal as a distributed system is a bit of code that will orchestrate these activities to come together and complete and over a potentially long period of time. So as an open source product and as a cloud service, we're super excited to have a lot of adoption on our cloud product, which is specifically what we're going to be talking about today, because this is what I work on. We're also super excited to count ClickHouse as one of our customers. So we're happily customers of one another. But today I want to talk about observability, because as a cloud product and as a thing that is running in the cloud, we naturally need to be able to introspect our own systems. And so when I talk about observability, it's kind of difficult to define what this word means. This word, I think it originally came from, factory line telemetry. But for us, kind of what we're meaning about here is we're talking about metrics, time series data, perhaps stored in a time series database, things like Graphite or Prometheus, things that your program is exporting in terms of telemetry in the format of time series. Logs, textual data, perhaps stored in a system like Logstash or Loki or Elasticsearch or these sorts of things. And traces, or these are like spans of program execution that you can link together into a graph and visualize. As I can see, we've got this helpful banner pointing to us about logs, events, and traces. Today, we're not going to be talking about traces, but we'll be talking about logs and metrics. Because Temporal Cloud is as a SaaS product, is highly multi-tenant. We have many different customers that are using our systems, many different tenants that are using our system, and we rely heavily on metrics and logs to understand the health of our own systems and also how our customers are experiencing our systems. Because of this, Temporal Cloud has deep requirement in our own observability systems, which is that we kind of need to always slice logs and metrics by tenant for pretty much for a lot of the telemetry that our systems produce. We want to know, for anything that's happening to our systems, what tenants are affected, how are they affected, what are the experience that particular customers are having. If customers are having specific issues, they open support tickets to us. We really want to drill down and see exactly what kind of experience that they are having. And to do so, we need to be able to slice all of this data by our tenants. Now, if you've ever had experience running time series databases, or particular ones like Prometheus or Graphite, you will find that all of the documentation and all the vendors everywhere will scream at you and tell you that cardinality is the enemy of your time series database. And specifically, cardinality is if you annotate your time series with particular labels, like For example, the host name of the machine that produced a bit of data, or a tenant ID, or maybe a pod in Kubernetes or something like this. That if you do this, and if you have different values for a lot of different values for each one of your labels, then the amount of time series data that your system produces grows quite a lot. And in fact, as you add new values into the power set of the Cartesian product of all of the different values that your labels can have, your costs increase linearly. And in our case, if you have a bunch of tenants coming into your system and you sometimes add new nodes to accommodate the new tenants, then sometimes the amount of metrics that your system produces is quadratic with the respect of tenants that you have. This is a huge problem for us and also for many other people across the industry. And if you read a lot of these posts about how you manage cardinality in these systems like this, a lot of them are, well, you have to go and prune down the data that your system is producing. This one right here is a blog post from our friends at Chronosphere. They say how quickly you can go from 150,000 possible unique time series to 150 million, just with a couple different changes that you make. So we have a problem here. We're producing a ton of data. We can't churn through it all. Our systems are flexing, and we need to start looking to change the way that we ingest high cardinality data. Before I worked at Temporal, I worked at Facebook. I don't know if there's any StatSig people here, but if there is a system that exists at Facebook called Scuba. I'm not going to go into too much detail about this today. There's a great paper about this called Scuba, Diving into Data at Facebook. And this is a really important system within Facebook because they have this paradigm of observability that I saw first at this company, which is that this is sort of like a database, but you can ingest data that looks more or less like a JSON blob, where you can submit to this system a data that looks like this. Like, for example, this is something that might represent a single web request in your system. Maybe it has a path, it has a user agent, maybe it has a timestamp when the event occurred, maybe also a duration for how long the request took. And with this system, you can throw this kind of arbitrarily structured JSON at the system, and what you get back is a table from which you can do select star from your table, and you get back a structured query. And you get back structured data. Where this really starts to shine is if you do something like this, you can, for example, select over the average of durations from requests where the user agent's a particular user agent and group by client version. So if you're going and debugging a problem, and you suspect that certain clients of your API that are using a specific version are having a bad time, you can go and query this data, specifically grouping by client version, and get back a response. And this is truly a transformative experience for an observability tool, because unlike a time series database system that is kind of eschewing cardinality, where they really don't want you tagging all of these different time series with data like your host names and tenant IDs, the system encourages you to do it and also lets you group by these high cardinality fields. So there's like three key properties about the system that are pretty compelling. It's schemaless and super simple to ingest data into the system. You just kind of throw JSON into it and it gets automatically ingested. And querying is super fast, real time. The idea is that this system is fast enough where you can issue exploratory queries. Like if you're working an incident, something is wrong, you need to quickly go and dive into your data and debug and see what's going on. The system is real time enough to quickly respond to your queries. And also this system stores raw events. So going back here, it's actually storing this data right here. It is not aggregating it. Aggregation occurs at read time, which means that you can do queries like this, or you can do different kinds of aggregations depending on what it is that you're trying to do. And this happens all on the fly. Now, there's a company out here called Honeycombio that took this idea and it's formed a company around this. And I'll talk about them a little bit more later on. But this is very much the idea of what they're going for here. And they also pull together some other bits across the industry, this is a blog post from Stripe talking about this idea of canonical log lines that they have, where in much the same way as this last example with Scuba and sending out log events, the folks at Stripe realized that at the end of a web request, if they logged a specially looking log line that looked kind of like this is just text, that has a bunch of fields on it, like alloc count equals 9123 or auth type equals API key, and then ingest it into a database, then you can do these really powerful queries like, if you want to know how many users are being rate limited in my system right now, I can do select count from canonical log lines where rate allowed equals false. And this, if you put this stuff into a database, you get these really incredible observability queries just from instrumenting your application. So you can probably see where this is going a little bit. Charity Majors, the CTO, co-founder of Honeycombio, put this quote in a blog post that she published recently. Where the world desperately needs an open source analog to Honeycomb, the system that looks very much so like Scuba. Something built for wide structured events stored at a columnar store or even just ClickHouse with an interactive interface. So hi, I'm here, we're talking about it. We're talking about how we solve this at this company. So for us at Temporal, we started looking at this problem of unbounded cardinality. And we started building a system that we called Chronicle, which had three main goals. Number one, removal of field cardinality as a scaling concern. As was mentioned before, when you add new tenants to your system, you can cause the number of metrics time series that your time series databases see kind of quadratically. We want to eliminate that entirely as a scaling concern. We want to be able to we want our observability system to embrace cardinality and ingest as much data as it possibly can and have this not be a scaling concern. Number two, we're really keen to add new query patterns that were previously impossible. Like this is something that is really important for our developer success organization. Whenever our customers are having problems, that we can go and dive into exactly the sort of problems that we have. We can see their requests. We can see what their experience is like in observing their systems, and we can have a really deep understanding of how our customers are experiencing things. And the third one is to play around with ClickHouse. Well, I'm kidding. Well, we just wanted to have fun with. We wanted to have fun with ClickHouse, but we already knew that it's a pretty spectacular piece of technology. So a little bit of how we did this is that one of the interesting things about Temporal Cloud is we support 14 regions. And all of the major cloud providers, except for Azure, shout out to Azure, will charge you anywhere from 2 cents to 9 cents per gigabyte of egress bandwidth if your bandwidth leaves an availability zone. That's a lot of money if you produce a lot of metric telemetry. And so we strive to keep data within the same zone from the moment that it is produced in an application service up to a point in which it gets to ClickHouse. And now we are customers of ClickHouse Cloud as we went here, which we chose for a lot of reasons, simplicity and performance being two key ones that I'll get into in a little bit. But we are using, we have 5 observability regions that we are running, where we collect observability data into 5 regions, and each one of these regions has a ClickHouse Cloud service attached to it via AWS Private Link. So we funnel 14 regions of data into 5 regions of little aggregation hubs, and then those go to ClickHouse. And the private link, we use private link here because bandwidth is 50% off for private link. They charge you 1 cent per gigabyte instead of 2, which adds up pretty significantly. So why do we do all of this? We did all of this for cost. We found that anytime our observability data leaves an availability zone, we incur a ton of costs. And so this whole design is informed by the promise of low-cost data transit and getting data to ClickHouse as cheaply as possible. Second, we also run a global ClickHouse cloud service in US West 2, which contains distributed copies of each database or each table that we have. We're using the remote secure table function to do this, and so what we're actually doing here is that we have these sort of link tables that we have in a global service that are all linked to the 5 regional cloud services that we have, such that whenever we do a query to the global one, it fans out and pushes down query predicates to the regional databases, evaluates them there, and then merges the results back at the top layer. Again, reason why we're really keen to do this is because of cost. There's been a ton of research and also just practical experience that if you have a bunch of data at a particular location, it is much cheaper to bring the query to the data than it is to bring the data to the query location. Because we get billed 2 to 9 cents per gigabyte of all bandwidth leaving a particular region. So because of this, we are utilizing this remote secure table function to go and and to receive global observability queries in our global database and push down all of the predicates and all of the smaller parts of the query, the regional bits of the query, to each individual region, evaluate the query in the region, and then merge the results back. Notably, ClickHouse does support this via the distributed table engine, but we don't use this because it's not currently supported in ClickHouse Cloud. But if you're running ClickHouse yourself, you can do this via the distributed table engine and accomplish roughly the same thing. And yeah, why are we doing this? For cost. We want we're trying to keep our data stationary and not leaving the availability zone in which it was created, so that we are not getting billed for data transfer every time data leaves it. Our schema is particularly tuned to our query patterns. So what I show here is a little bit of a partial table schema for some of the data that we are persisting in our system. These are some logs that are coming from our load balancers. So if you're familiar with like Nginx ingress logs or Envoy logs, this is very similar. There is a record or a row in this data set for every single request that goes through our system, with a whole bunch of information on it, like which cluster, which region, which zone it originated, the tenant's ID, how bytes received and sent. There's a whole bunch of useful fields here. And we call this a raw table because there is exactly one row per request. And this is exactly like in Scuba and Honeycomb. This is what they're talking about with a wide structured event of our canonical log line. There is exactly, these correspond one-to-one with requests in our system. Our sorting key is really important here because we chose our sorting key to sort order by cluster, then to order by namespace, and then to order by timestamp. This means that if you do a select star from this table without filtering on the cluster or temporal namespace, which is our tenant ID, you're probably going to have a slow query. But this is based on our experience with raw tables, which is that our customers really that are doing these sorts of queries want to filter to target a particular environment, like a particular place for this where data is being produced, and also by tenant ID, and then group by namespace. So we found that this ordering of our choice of ordering key provided really solid performance in the case where people are doing these sort of investigative style queries in our system. Something that is very kind of unique for us in this realm of system is that we perform a lot of write-time aggregation by utilizing materialized views within ClickHouse. So if you read the Scuba paper and also some of the documentation that Honeycomb has written about their public system, they say that you should be storing raw events and you should only be doing read-time aggregation. They say the reason for this is that sometimes you really do want to go into these raw tables and want to look at it, a single web request or a single set of web requests. ClickHouse kind of lets us do both of these things at the same time, which is pretty incredible. So when we are inserting into ClickHouse, we insert data into our raw table, which is the table that has one record per event that we're going in, and we also insert into using some materialized views other tables that perform some like aggregation. One thing that we have right here is we have a table that is aggregating the histogram for the request duration. And the end result is that we are able to do these sort of heat map style queries. If you've never seen a visualization like this, this is a kind of like if you take a histogram and lie them all one after another and then look down upon them, where a hotter color here represents a taller histogram. This query finished in about 50 milliseconds across our entire fleet. It leads to like true real-time performance, and we use this to optimize common dashboard queries such that dashboards load almost instantaneously. And we can do this because the ClickHouse materialized view operation is relatively cheap in the grand scheme of ClickHouse ingestion compute that we send. Performance. So across the system, we've found that we've been able to push ClickHouse Cloud to one core produces 45K rows per second. We've seen as high as 60K. And inserted rows per core per replica hover between 100K and 150K rows per second. So this is, we're able to use some of ClickHouse Cloud's smaller, or mid-tier compute instances to ingest quite a lot of data. A key part for us is that we use async inserts with a 5-second wait period. Async inserts were wildly important for our insert performance. We found by enabling it with a 5-second wait period, we were able to ingest substantially more data with the same compute profile. Our write aggregate tables generally return within queries within about 200 milliseconds. These are the really hot queries, things that are serving things like our like P99 request latency and the heat map that I showed you. Extremely fast. Our largest table achieves a compression ratio of 36.59x times. That's 3 times what the ClickHouse website advertises as what you will see when compressing your data. Largely to the pretty extreme compression ratios that we get by compressing our tenant IDs and other strings that we are sending through our system. A lot of the strings that we're sending through our system are things like AWS region names and AWS zones. And the tenant IDs themselves, and these are all just extremely compressible strings when dictionary encoded, which ClickHouse is doing. Going back to our schema, we've marked all of these with the low cardinality modifier, which, from ClickHouse's perspective, basically every string that we put into our observability system is considered low cardinality. So they compress extremely well. Our data point column, which is for columns that are representing like samples of data, like floats, we get a compression ratio of 2.63x. This is the best that we did just by tuning. We're actually using the decimal type instead of floating point with zstd compression. We toyed around with the Gorilla encodec and double delta encodings, and we were not able to beat 2.63x. But in practice, this has worked really well for us. And the write time aggregation for ClickHouse has been particularly impressive for its query performance and making dashboards appear really snappy internally. So yeah, a couple things that we would love that like dream features of the system that we currently don't have. One of the things that's really compelling about Scuba and Honeycomb and other tools in this space is that you get truly schemaless ingestion. Like you can just throw JSON at it, and the table engine will figure it out, and it will serve it to you in a performant manner. A lot of our engineering resources have gone into schema management of these tables, of making sure that their schemas are what we expect them to be, and also managing changes to these schemas as new fields get added and whatnot. And we did choose to fully schematize our tables in the name of performance, which is or choosing our ordering keys, but with as much freedom as we can. We might change this in the future. We're not fully decided, but at least we were shooting for performance at the start, and that's why we chose a full schematization. Secondary is lack of separation of compute pools is kind of a problem for us. Right now, we use we have regional ClickHouse cloud services, and if somebody runs a bad query on one of them, then ingestion will screech to a halt as the ClickHouse service will spend all of its compute trying to service the bad query instead of starting to handle inserts. This has caused some incidents for us. We really, really want to have separate compute pools for ingestion and ingestion and query, so that people can write bad queries, and that's fine. It just means that they will deny the query pool, but ingestion will continue. We really love to have separate compute pools for even different kinds of queries. Like maybe there are some queries that have different quality of service levels. Maybe alerts run at the highest possible query quality of service, and maybe the lowest possible quality of service might be a data pipeline. But it'd be really compelling if we could go and separate all of these things and have different policies for each. So thank you all. Appreciate you listening to me talk about observability today. I do want to leave you with a couple other links about observability. Both of these were authored, I believe, by Charity Majors and associated with Honeycomb.io. I think they're really excellent reads about observability and go into a lot more detail of what I was talking about at the beginning of this talk. This quote, I think, sums up why I'm super excited about our use of ClickHouse at Temporal, and it's about understanding not just our bugs and outages, but proactively understanding our software and how our users are experiencing it through the raw data that we can collect and query efficiently through ClickHouse.